All right, well, here's the setup for our bungee activity. This whole center section here is really just the support structure, okay? And what I have here is a 200-gram mass, and what I'll be doing is I'll be holding this right here. Whoops, sorry. I'll be holding this right here. This is 1.48 meters above the ground. All right, so we got some gravitational potential energy, and we can figure that out really quickly. And what you see here is that the mass is hanging at least 20 centimeters above the water. And the water level is 4 centimeters above the ground. Okay, so that's going to be an important piece of information. The key here is for the students to figure out what the spring constant is in this spring. And ultimately, how far that spring will extend. The extension of the spring will determine how long the string should be. All right? And I'll just show you an example of how this should work. The idea, of course, is for the bungee jumper to survive the jump, hit the water, but not go so far as to hit the bottom of the pan. And let's try it out. So 3, 2, 1. There we go. Whoa, hey, stop. I would call that a successful bungee jump. All right, well, let's take a look at how we actually figured out the spring constant. What I have here is a dual range force sensor. And really all I need to do is hook my little spring onto here, onto this hook, and calibrate the software and say, hey, when I start pulling on this, I want you to record how much force is being applied to the sensor. And what I've done here is I took 4 different data samples. Okay, and what I found was that in order to get this thing to stretch 0.05 meters, 5 centimeters, it took 4.7 newtons of force. And there you can see 10 centimeters, 8.4, 15 centimeters, 11.9. Okay, and what I did was I just plotted that into Sheets or Excel, one of those kinds of things, and I graphed the slope. Well, actually, I didn't. All I really did was I knew it was going to make a straight line, okay, a line of best fit. And really all I did was I took the delta y, divided it by the delta x, the rise over the run, and I got a number close to 74.2 newtons per meter. That is the spring constant of the particular spring that I used. And now that I know the spring constant, with a little help from the conservation of energy, I could then figure out how far that spring would stretch. All right, well, this looks like a mess, but we're going to step through this in an organized way. What I tell my students to do is like, okay, you know what, let's draw a picture of this problem. And we'll take a look at the beginning, we might take a look at the middle, and we'll take a look at the end. So at the very beginning, okay, I've got this 200-gram mass, and I know that it is 148 centimeters above the ground. All right? And so I just do a little MGH, and I get the fact that this 200-gram mass has 2.9 joules of gravitational potential energy before it starts to fall. Now, right here, right in the middle, where it reaches the end of its rope, I've got some gravitational potential energy left. I'm not sure how much, because what I'm really ultimately trying to find right now is how long that string needs to be for this thing to just touch the water, okay? Well, I don't really care about this intermediate step right here. It doesn't matter to me. What I want to do is I want to go down to the very bottom. So at the very bottom, where this mass has now reached the end of its rope but starts to extend the spring, it has just a little bit of gravitational potential energy because it's not going to travel the whole 148. I don't want the little mass to hit the ground. It's only going to go 144 centimeters. All right? I want it to just barely touch the top of the surface of the water, which is 4 centimeters above the bottom of the tray. Okay? So now, and oh, by the way, I know that the velocity at the very bottom should be 0, hopefully. And that's where it then starts to go back up. All right, so now I know this. So I can solve now for the amount of energy that has to be stored in the spring when I have 0 velocity. Pretty cool. Okay, and that ends up being 2.83 joules. Okay, really important piece of information. Bam. Now I can go over here. Okay, and there's a summary of what I've done. But now, right, we have our equation for elastic potential energy. U sub s, in this case, equals 1/2 kx squared. Well, I just determined how much energy that spring should have within it when it's extended. And I found the spring constant, doing a little bit of testing. And now look at what we have. The delta x, and I decided to leave everything in centimeters for this problem. I'm not sure why. The delta x here, okay, in my spring potential energy formula, becomes 27.6 centimeters. Whew, all right. Now, let's go over here. Here's what we know. Here is what we know. And this is one of the things that the students will always have a problem with, because they will usually forget how tall the mass is. All right, and that 8 centimeters can be the difference between life and death, right? So I really want this thing to fall 144 centimeters. I know the height of the spring before I start pulling on it at its equilibrium, happy place, is 14.5 centimeters. The mass is 8 centimeters tall, and I just found how far the spring should stretch. I solved this now for the length of the string. The length of the string, and I should have had that just be an ST, the string should be 94 centimeters long. And here's my picture, right? I've got the spring, 14.5 happy place, plus an extra 27.8 when it stretches, and I have this 8 centimeters, okay? So I need 94 centimeters worth of string. And if I cut that 94, attach it to the mass, attach it to the spring, and let it fall, oh my gosh, success. This is a lot of fun. My gosh, we've got the conservation of energy, all right? And a lot of times, you know what? A lot of times we don't cover springs in a way that that really makes it understandable. It's really a very easy concept. Okay? Now realize, if you're going to use rubber bands, rubber bands do not really adhere to this. All right? Just realize that. Springs, much better choice. And you can actually buy springs that have a well-defined spring constant. You can actually order them so that they have a particular spring constant. But in this case, I don't care. I don't care what the spring constant is. That's what makes it fun. They need to figure it out, right? And the most important thing is whether I have a spring constant of 80 or 90 or 125, all it means is that I have to have an either longer or shorter piece of string in order to make this bungee jump survivable. I hope you guys have enjoyed this, and I hope it was valuable.
Splash.